Welcome back to Digital Systems 1. In this video, we are going to discuss parity circuits and enable/disable circuits. So by the end of the video, you should be able to describe the truth table, the symbol, and the expression for two new gates that we have not talked about before. Those gates are the XOR, which stands for exclusive OR, and the exclusive NOR gates. So we're adding two more gates to our repertoire today. And we're going to use those gates to evaluate the operation of a parity generator and a parity checker circuit. You'll remember parity is something that was discussed during the first day of class, and we're going to revisit that idea today and learn about some different types of circuits that will be able to generate a parity bit or check the parity of a string of input bits to see if there is an error in the inputs. Lastly, we're also going to learn how to design and enable or disable circuit. In the previous video, we started talking about the design process and using K-maps to complete that design process. We're going to continue that discussion today by learning how to design an enable or a disable circuit. First, I'll begin by going over the two new gates we're going to use in today's lecture. The first one is called the exclusive OR, and we use the letters XOR for short, the exclusive OR gate. On the screen, you'll see the symbol for the exclusive OR gate. It has two inputs, A and B. It's got an extra bar right here in front of the OR symbol. That lets us know that it's an exclusive OR gate. And the truth table for the exclusive OR looks like this. If A and B are both low, or if A and B are both high, the output is low. The output is only high if A and B have different values. If A is 0 and B is 1, or if A is 1 and B is 0. That's how an exclusive OR works. It only has two inputs, and when you combine those two inputs with the idea represented in the truth table, your output expression is not A and B, or A and not B. That's the expression that we have for exclusive OR. A shorthand way to indicate the XOR expression is to use this symbol right here. It's like a plus sign with a circle around it. Anytime we see that symbol, that lets us know that exclusive OR is implied within the expression. And once again, the exclusive OR only has a high output when the two inputs are at different levels. That's the exclusive OR gate. Inside of the exclusive OR, it would literally be wired like this picture right here on the screen in picture A. Remember, the output expression for exclusive OR is not A and B, or A and not B. So if we literally were to wire this expression, we'd have an inverter for A going into an AND gate with B. We'd also have A going into an AND gate while B gets inverted. And then the output of those two AND gates would go to an OR gate. That's how we would create a circuit to implement the idea of exclusive OR. So whenever we see this symbol on a schematic in the textbook in Multisim, what's really going on inside of this particular circuit is this orientation right here. This is the circuit that's going to produce a high only when the two inputs are at different levels. Next, we have the exclusive NOR gate. So you can see that we have the same symbol as before with an extra bar right here in front, but an exclusive NOR gate has a bubble on the end. Remember, the bubble always denotes inversion. So the exclusive NOR is going to work in the exact opposite fashion as the exclusive OR. You'll see here in the truth table below that the exclusive NOR gate only has a high when both inputs are the same. If both inputs are at different levels, the output will be low. Here's how we represent exclusive NOR. It basically looks exactly like exclusive OR, but with an overbar over the entire expression. And what that literally translates to is that it's equal to A and B, or not A and not B. And we can see that from the truth table here. If we were going to write the SOP terms for this truth table, we'd have not A and not B, or A and B. So the XOR gate only has two inputs, just like the XOR. When you combine them, this is your output expression right here, A and B, or not A and not B. And the way that we would indicate that with shorthand is to use that same symbol that we have for XOR, but with an over bar across the entire group to represent the inversion. And the main idea for an XNOR gate is that the output is high only when the two inputs are at the same level. Internally, here's how the XNOR gate would be wired. You'd have to have two inverters to invert both A and B and send that into an AND gate. Meanwhile, you'd also have to send A and B without being inverted into a second AND gate. And then you would combine those together into an OR gate. So anytime that we see the XNOR symbol, we can imagine that this is really what's happening internally in order to produce the output shown in the truth table, where the output is only high when the two inputs are at the same level. So, in your notes, you have a circuit that looks like the one on the screen, and I want you to try to simplify that circuit below by implementing either an XOR or an XNOR gate. So we did a lot of simplification in the last two videos. What I want you to do is to pause this video now and try to simplify this circuit. Remember, to simplify, we begin by writing the expression for the output and then trying to use Boolean algebra to manipulate that into something simpler. So take a second and see if you can come up with a simpler circuit that would use an XOR or an XNOR gate. And here's the solution to this particular circuit. We're going to start by writing the output expression for the circuit. I'm going to begin with the AND gate right here. Notice that A, not B, not C, and D go into the AND gate. So that's what's coming out of the AND gate. A and not B and not C and D. Notice with the blue AND gate here, we have D going in along with C, along with B, along with A. So now we have A and B and C and D coming out of this AND gate. And then down here we have a NOR gate. And going into the NOR gate, we have A and we have D. Keep in mind that the expression right here has been written after De Morgan's theorem has been applied. If you're wondering why doesn't the output look like this, that's because if you apply De Morgan's, break the bar, change the sign. Oh, I'm sorry, that should be a D. Should be a D here. So if you're wondering why doesn't this particular label say A or D as a group inverted, that's because it's just written after De Morgan's has been applied. Break the bar, change the sign, and you'll end up with this expression here. So you could write this either way, but eventually you're going to have to apply De Morgan's for simplification purposes. So this is just cutting that one step out. So all three of these are inputs to an OR gate, and our final output expression is going to be A and not B and not C and D, or A and B and C and D, or not A and not D. Now we're going to simplify this. So here's the expression we started out before. We're going to use those Boolean theorems to see how we can make this term simpler. Notice that the first two terms both have an A and a D. Both terms, the first two terms have an A and a D. So let's factor that out. Here's what you would have left. And this is where you really have to understand the output expression for no XOR and XNOR. Right here is where we can identify a place where XNOR can be substituted. We have B and C, or not B and not C. That's the idea of XNOR. This expression is going to be true if B and C are both 1 or if they're both 0. So this is an example where an XNOR could be inserted to replace this piece. So once we insert the XNOR right here, this becomes our new simplified expression. We have A and D and the quantity B XNOR C, or not A and not D. So let's take a look at what that circuit would look like if we simplify it by putting an XNOR in for this piece right here. So now here's our simplified circuit where the XNOR is right here. And then we have that going into an AND gate with A and D. We also have the NOR with A and D as the inputs to the NOR. And then the last two expressions are going into an OR gate. So this is our simplified expression and our simplified circuit. Keep in mind, that's what we started with on the right. On the left is the simplified version. So we eliminated this AND gate and these two inverters and instead replaced them with one XNOR gate. So it's slightly simpler because it has fewer gates. So whenever you're simplifying and you're applying Boolean algebra to a simplification process, you're going to want to look for a time when something like this pops up, or you're going to want to look for a time where it says B and not C, or not C, not B and C. You're going to want to look for those conditions where XOR and XNOR would apply. Next, we're going to look at some applications of the XOR gate. One application could be a circuit that generates a parity bit. Remember that a parity bit is a bit that is attached to a message, a string of bits that is being sent or transmitted in a system. And we use the parity bit as a way to determine if there's been an error in the message that's being sent. So this particular circuit is an even parity generator. So it will generate a parity bit based on the idea of even parity. And the input data is going to be supplied right here, D3, D2, D1, D0. And the output is just going to give me what the parity bit should be if I'm going to use even parity. So let's take a look at some examples of how this would work. In the first example, D3 is 0, D2 is 1, D1 is 1, D0 is 1. So I'm sending the message 0, 1, 1, 1. If I'm going to be using even parity, I would need my parity bit to end up being a 1 so that I have an even number of 1s in the message. Well, let's work the logic to see how that's going to happen. So with this first XOR gate, a 0 and a 1 goes in, and a 1 would come out. Remember, an XOR will give you a high if the inputs are at different levels. With the second XOR gate right here, a 1 and a 1 goes in, and a 0 will come out because those inputs are not at different levels. They're the same level. The third XOR gate now has a 1 and a 0 as its inputs, which means it will output a 1 because the inputs are at different levels. And your parity bit ends up being a 1, just as we expected, and the message that's going to be transmitted will then be 1, 0, 1, 1, 1, with an even number of bits because we're using even parity. Let's take a look at the second example in your notes. Let's say now that the data inputs are 1, 0, 0, 1. So with this particular group of data, we can see that there's already two 1s in the group, and the parity bit should come out to be 0. Let's verify that this is true. Coming out of the first XOR gate, you've got 1 going in with a 0. Those are at different levels, so you'll get a 1 out. And the same thing with the second XOR gate right here. A 0 and a 1 go in, so a 1's going to come out. With the third XOR gate, both inputs are at the same level, so a 0 is going to come out. And our message ends up being 0, 1, 0, 0, 1, exactly as we expected it to be, based on even parity. So this particular circuit will generate your parity bit. Now it's made for an input of 4 bits, but you can increase the input bits. You can make this for a data set that's larger than 4 bits, but the concept will remain the same. This particular network of XOR gates will generate your parity bit for even parity. You can also use the XOR gates to create a parity checker that will check the parity of an input and produce a 1 at the output if there's an error in the message, or a 0 if there's no error in the message. So now we're going to see how this particular circuit works using XOR gates. Notice the inputs. The first bit here is your parity bit, and then this is your data that comes in from your transmitting system. So let's look at the first example and explore how the even parity checker would work to determine if there was an error in the message. You'll see in your notes that the first data that you have is with a parity bit of 0, D3 is 1, D2 is 0, D1 is 1, D0 is 0. So we have the message 0, 1, 0, 1, 0. If this is an even parity system, I can see that there are 2 1s in the message, and I should get that there's no error. Let's verify that this is true. Starting with the first XOR gate here, the inputs are at different levels, so the output will be 1. Same thing with this XOR gate. The inputs are at different levels, the output will be 1. With this XOR gate, the inputs are the same level, the output will be 0. And this 0 goes into the final XOR gate with the parity bit, which was 0. These are the same level, so the output here will be a 0, letting us know that there's no error in the message. So this circuit can very easily check your parity for a message and determine if something might be wrong. Let's take a look at another example with the parity checker. This time your inputs are 1, 1, 1, 1, 1. 5 1s. So if I'm in a system that's supposed to be using even parity, I should have an even number of 1s, and I don't have that. So I'm expecting this circuit to produce a 1 to let me know that there's an error in the message. Let's verify that this is the case. So start with the first XOR gate right here. Both inputs are at the same level, so you're going to get a 0 out. Same thing with the second XOR gate. And the same thing with the third. Both inputs are at the same level, so the output is going to be low. That's based off of the truth table for an XOR gate. Lastly, this 0 goes into the XOR gate with the 1 from the parity bit. Now the inputs to this XOR gate are at different levels, and a high will be produced, letting us know there is an error in the message because it does not have an even number of 1s. So this is another application of XOR gates by creating a circuit that can check parity. Next, we're going to talk about enable and disable circuits. And these situations occur very frequently in digital circuit design. Imagine a time when you want to enable a signal to pass, and you might want to block a signal from passing. We call a circuit enabled when it allows the passage of an input signal to the output. We call a circuit disabled when it prevents the passage of an input signal to the output. And when we say an input signal, we're going to think of a signal that's changing over time, not something that's always high or always low. So for example, imagine you have an AND gate. Your input A is connected to a signal that creates a square wave. It's high and then it's low, it's high and then it's low. It's continuously changing with time. If the other input to your AND gate is a 1, the output to the circuit will be whatever A is. We learned that in our Boolean theorems. Anything and 1 is itself. So the signal that goes in will be the signal that comes out. However, if we take that same AND gate and tie that second input to 0, we know that the output will always be low, no matter what the other input is. We also learned that as one of our Boolean theorems. And we would call this a disabled circuit because we're sending in a square wave signal and we're getting a constant low out. The signal is disabled. Here's another example of enabled and disabled. If you have a NAND gate, and the first input is tied to 1, well, the input B is tied to 1, and your input A is your signal, what's going to come out is the same input but inverted. We would still say that's enabled because the signal is passing. It's inverted, but it's passing. However, if you take a NAND gate and you tie that second input B to 0, it doesn't really matter what A is going to be. If one input to a NAND gate is low, the output is always going to be high. So even though the output is high, we still say this is disabled because the output never changes. I'm sending in a signal and I'm getting a constant output out. So we don't think of disabled as when the output is low. We think of disabled as when the output is a constant value that doesn't change even though my input is changing. No matter what happens at A, I'm never going to get anything but a 1 out. That's a disabled signal. The signal goes in and I get a constant value out. So don't think of disabled as the output has to be 0. Just think of it as the output is constant and never changes no matter what's happening with your input signal. Another example of enable and disable using an OR gate. If you have an OR gate and you tie input B low, then the output will be whatever A is. If A is high, the output will be high. If A is low, the output will be low. So the signal that you send in will come right back out. And we say that that signal is enabled. But if you take that same OR gate and you tie input B to a high, you make it 1 always, doesn't really matter what A is, the output is always going to be 1, which means that signal is disabled. Again, it doesn't matter that the output is high or low. What matters is that the output never changes, no matter what happens at the input. So this is a disable circuit because input A cannot be seen at the output. And then lastly, you can also do enable and disable circuits with a NOR gate. If you have a NOR gate and one input is tied low, then your signal will be seen at the output but inverted. So we still call that enabled, but it's enabled and inverted. With a NOR gate, if the second input B is tied high, it doesn't matter what A is. If one input to a NOR gate is high, the output is automatically always going to be low. We call that disabled. So those are some examples of how we enable or disable a signal using these particular gates. Now let's figure out how to design a logic circuit that will allow a signal to pass to the output only when the control inputs B and C are both high. Otherwise, the output will stay low. So keep in mind that this problem description tells you that there are control inputs, B and C. They both have to be high. We're going to consider input A to be our signal. Just like in this diagram here, input A was a signal. It went 0 to 1, 0 to 1. It's a square wave. It's a signal that's changing with time. That's the signal we want to pass, only when B and C are both high. Otherwise, the output will stay low. We're going to use this problem description to first set up the truth table for this circuit. So we know that when control inputs B and C are both high, that would be here and here. Those are the times where the input signal A is going to pass to the output. If B and C are both not high, the output will stay low. So, for the first 3 rows of your truth table, the output has to be low because B and C have not met the condition. They're both not high. When you get to the 4th row, When B and C are both high, the output must become whatever A is. A is currently a 0. So the output will become whatever A is. You're not going to put a 1 here just because B and C are both high. The signal has to pass. Whatever the signal is at this point in time is what will pass because B and C are both high. So you're going to put a 0 here. With the next 3 rows, you can see that B and C do not meet our condition, so we know that the output must be low. And with the last row, B and C are both high. Whatever A is will then pass to the output. So essentially, we get a truth table where there's only one time that the output is high. When A is high, while B is high, while C is high. That's it. That's essentially just a 3-input AND gate that will allow the signal to pass whenever B and C are both 1. So when B and C are both 1, whenever A is 1, the output will be 1. Whenever A is 0, the output will be 0. And you'll have a wave at the output that looks just like the input. This is how we design an enable circuit or a disable circuit, by following the conditions provided in the directions and noticing that whenever the conditions are met, whatever is in A at that point in time is what goes to the output. Let's do another example. Now we're going to design a logic circuit that will allow a signal to pass to the output only when one, but not both, control inputs are high. Otherwise, the output will stay high. So one, but not both, control inputs are high. That's our condition. So remember, A is our input signal. That's the signal that we want to pass to the output. B and C will control that signal and allow it to be enabled or disabled based on the problem statement. So whenever one but not both control inputs are high, that would be here and here and here. Those are the instances where whatever A is, A should pass to the output. And then in any other instance, the output should be high. So for the first row, the output is going to be high based on the problem statement. For the second row, this meets our conditions for the control inputs. One is low, one is high. That meets the conditions. So whatever is in A goes to the output. Same thing here. This meets the conditions, so whatever is in A goes to the output. For the next row, B and C do not meet the input conditions, so we know the output has to stay high based on the problem statement. Same thing for this row right here. Now, we've entered another case where B and C meet the control conditions, and now whatever is in A goes to the output. Same thing here. Whatever is in A goes to the output. And in this case here, the very final row, these two inputs do not meet the control conditions, so the output must be high based on the problem statement. Once we have our truth table, now we're going to write an output expression and simplify it using Boolean algebra or using a K-map. I'm going to do a K-map because it's much quicker and much faster. Here's what the K-map is going to look like. Remember, you're going to set this up with 8 cells. You're going to label the outsides just like we were discussing in the previous video. And you're going to fill in the outputs based on your truth table here. And then you're going to make your circles. You're going to have 3 circles. A group of 4 at the bottom. A group of 2 top and bottom. A group of 2 in the middle on the right. Your expression here becomes A, that's for the big square, or not B and not C, that's for this circle right here, or B and C, that's for the third circle. Now, the output from the K-map is not going to tell you that this is XNOR. You have to know that by knowing what the expression for XNOR looks like. So you would have to know, you'd have to memorize what the expression for XNOR looks like to realize, oh, I can implement this with an XNOR. So this is inherent knowledge here. But that's what your output expression is going to become. A or B XNOR C. Here's your circuit that will implement this design. So when you go to build this circuit, you will see that if B and C are both high or both low, the output here will always be high, which means it's disabled. But when B and C are at different levels, the signal will pass and you'll see a square wave coming out of the output instead of a constant low or high. That's how disable and enable circuits work.